Hello everyone, this is Nitin and I am an assistant professor of mathematics from the Department of Mathematics, and we are going to start the topic calculus of variation. In this calculus of variation, we are going to start the functionals. Functionals, what are the functionals? Functionals are the functions of functions, mean that function f is also a function, and in f there is x, y and y dash, and y dash is also a function. So functionals are the function of functions, and in this we are going to start. First of all, this is a curve in which there is 2 points a and b, and we are going to find the minimum length between the points a and b. Or for this we are introducing this functionals, and after that we start in this problem. Just a minute. We are introducing Euler's equations. Euler's equation. This Euler's equation, a necessary condition for I equals to integration x1 to x2 f of x comma y dash dx needs to be minimum is that del f upon del y minus d upon dx del f upon del y dash needs to be 0. This is the condition. This is the Euler condition in which a functional is minimum if this is 0. Okay, and the solutions, there are lots of conditions for the Euler's equation. First condition is that if when f is independent of x. Independent of x means del f upon del x is equals to 0. If del f upon del x equals to 0, then Euler's equation becomes d upon dx f minus y dash del f upon del y dash equals to 0. This is the condition, and on this condition we are going to start a question. Let me explain this condition with a question, and question is that we have to find the extremals of the functional. We have this functional x1 to x2 y dash square upon x cube dx. This is a functional, and we have to find the extremal or minimum of this function. So for this solution, we start solution. Here we have f equals to y dash square upon x cube. This is a functional, and it is here f is independent of y. If it is independent of y, then that is del f upon del y is equals to 0. This is the condition in which if f is independent of y, then del f upon del y equals to 0. Also, d upon dx del f upon del y dash is equals to d upon dx. We write this function, but we have to differentiate it with respect to y dash. This is the function, and this is the differentiation of f with respect to y dash. When we differentiate it, we have 2y dash upon x cube. When we are going to do this type of differentiation, we assume that rest of the functions are constant. So that's why there is a differentiation of only y dash square. We don't touch it. For this 1 upon x cube becomes out from the differentiation. Only we are going to differentiate this y dash square. So y dash square differentiation 2y dash upon x cube. Okay. Then after that we are also going to differentiate it function. So we know that divide rule of differentiation. What is the divide rule of differentiation? First of all, we square this x cube square, then x cube differentiation of 2y dash minus, we keep 2y dash as it is, then differentiation of dy dx of x cube. Okay, after this we continuing it. This x cube square means x to the power 6, x cube as it is, the differentiation of 2y dash. The differentiation of 2y dash is 2y double dash. Okay, 2y dash as it is, then differentiation of x cube, then differentiation of x cube 3x square. And in this we seen that there is a x square common, so we kept it out, x square. Then here we have 2y double dash x minus 2y dash. Okay, and upon x ki power 6. And after that this cancel out. Then we have 2, we also kept out 2 common, so 2 upon x ki power 4, then y double dash x minus y dash, okay, sorry, 3y dash, sorry, 3, here is 3y dash. Okay, so we have this one. And after that we have this is, so Euler's equation reduces to, Euler's equation reduces to d upon dx del f upon del y dash is equals to 0. Here 2 upon x ki power 4 and x y double dash minus 3y dash is equals to 0. Okay, we are going to solve this. This is the this is x ki power x raised to the power 1 upon x raised to the power 4, x y double dash minus 3y dash equals to 0. Okay, we move this to 0, then we have x y double dash minus 3y dash equals to 0. After that x y double dash is equals to 3y dash. After that y double dash upon y dash is equals to 3 upon x. Now this is a differential equation. This is a differential equation and we are going to solve this differential equation. So for this, solving this differential equation, we integrating it. We integrating with respect to x. We integrating this above equation with respect to x. So when we integrate it, the integration of y double dash upon y dash is, for this integration we put y dash equals to t, y dash we put t, then after differentiating y double dash dx is equals to dt, then the above this integration becomes y double dash dx is dt and this is upon t is equals to 3 upon x. Yeah, okay. Now on integrating, we integrate it, it is log t equals to 3 log x, and we introduce here the constant of integration, and the constant of integration is log c. Okay, now we solve this, we put the value of t, here we put t y dash, the y dash equals to 3, and is the property of log, if there is something behind the log then it comes raised to the power. Okay, so log x cube plus log c, log y dash, and this when there is addition between the log then it turns to x cube c, and here log both side cancel out, we have y dash equals to x cube c. Now this is also a differential equation, so we have also integrate, mean that on integrating again with respect to x. Okay, we are going to introduce it and integrate it with respect to x. Then y dash equals to the differentiation of y dash integration of y dash dx is equals to integration x cube c plus there is a constant of integration c dash. Okay, then differentiation integration, as you know that it's cancel out, so then we have y is equals to, and the integration of x cube is x raised to the power 4 upon 4 c plus c dash. Okay, as this is also, we can just reduce it, this equation. So x power 4 as it is, this is c upon 4 plus c dash, and y equals to x ki power 4, and we name this another constant c1, and this is c2. So this is the function, and this is the equation which reduce the given function, into a extremum form. So we have this one, this is the example, and we have some more form of Euler's equation. Just we started, I just give you a knowledge about that. First of all, we just know when f is independent of x, then del f upon del x, as I told you in this topic, hence del f upon del x equals to 0. Then the Euler's equation becomes d upon dx f minus y dash del f upon del y dash equals to 0. Then here f minus y dash del f upon del y dash equals to constant. This is the property of integration when there is a differentiation and we have equals to 0, no? When we integrate it, then this 0 becomes constant. So we have, this is the another form, but only this form is used when f is independent of x. This is a one form of Euler's equation. Okay, so we'll introduce some another form, second form, when f is independent of y. Okay, when f is independent of y, same, del f upon del y equals to 0, and Euler's equation becomes, we have Euler's equation d upon dx bracket del f upon del y dash equals to 0. अब on integrating we have same, del f upon del y dash equals to constant. Okay, when del f upon del, and it is easily directly integrable, and after integrating we have solution. This is second form. Okay, and after that third form is that when f is independent of y dash. We have some several functions which are some are independent of x, some are independent of y, and some are independent of y dash. So with these solutions we can easily solve them. Okay, when f is independent of y dash, del f upon del y dash equals to 0, and Euler equations become and Euler's equation becomes del f upon del y equals to 0. Del f upon del y equals to 0, and this del y upon del y upon del f f upon del y equals to 0 gives direct solution. So these are the different types of Euler's equation in which we can easily solve the functionals. Thank you so much. Thank you everyone.